All right. Oh, I can also record. Okay, thank you.
Okay. So today I hope to give only 2 hours. Pasha, you know that I always hope to give 2 hours, but it happens that it goes to 3. Still, I have quite a special topic today related to the study of this equation, commutativity equation, that I'll rewrite again.
Andrei, it's not focused on the board.
Not focused. Because I cleaned the board. Okay, 1 second.
Okay, yeah. Oh, that was good for a second there. Okay, good.
Okay. So the goal
now it's back. It's back to unfocused. Maybe you can do these crosses. Maybe that will help. Okay, now it's good. Now it's good.
Okay, so so the goal of my today's talk would be to discuss the following 2 unrelated topics, naively unrelated topics. Topic 1, dressing transformations. Topic 2, tensor products. And let me give a conjecture. And I'm quite sure that it's true, but I don't know a way to prove it. And conjecture is that you might take solution to this equation. I don't know how to call it. This solution, you may call it A. And then you might do the following thing. You can take one A, and I'll explain what does it mean. Tensor product it with the second A over the space Lm. And then you can dress. And you get dressed. A1 tensor A2. You can also do the following. You can take A1 and dress. You can take tensor product over Lm. Okay, it's better to write it like this. You can have 2 dressings. And then you can take a tensor product of the dressed. Dressed A1 times dressed A2. Over Lm. And the conjecture is that you have the same thing. So, we will discuss this mysterious dressing transformation that seems to be compatible with a tensor product. And when I say tensor product, how should you understand it? Like tensor product for infinity structures. And when I'll discuss this tensor product, I'll recall what does it mean to have this tensor product for two so-called physical systems. And there is also homological definition of this tensor product. Such tensor product that I'm going to talk was observed by Kyoji Saito in the theory of primitive form when he had two singularities, W1 of set XA1, okay, XAN, and also W2 YA1, YAN. In the theory of primitive form. This tensor product was almost found by Kontsevich and Manin. When they studied Gromov-Witten for x1 times x2. I say almost because here there is another tensor product. This tensor product would be related to Derinь-Mumford space.
So the bottom is a little bit out of the frame.
Derinь-Mumford space. And I'll also discuss this. Now, point number 4. There was a reconstruction equation that allowed to make from A, that is equally d tau, solution to oriented WDVV. And it turns out that reconstruction is compatible with the tensor product. And I also only have conjecture here that is verified by general reasoning, blah, 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 and test computations. But I do not have the proof. So let me say, Pasha, you always wanted that from my talks there would be kind of particular problems to solve. So here it's a purely mathematical problem. And as far as I understand, people who are not studied, had not studied it. So here are two conjectures. So it would be nice to prove something about it. Okay? So the field that I'm discussing is called so-called cohomological field theories in dimension 2. You see, it is the standard name. This name, as people explained to me, was introduced by Schwarz, I mean Albert Schwarz. However, I prefer systems that has even more information. So I prefer to speak about higher topological quantum field theories. Just to explain. Also, these tensor products could be generalized to disk with marked points on the boundary and marked points inside. And here it would be Fukaya times Fukaya. And here is the answer to Dong's questions. Suppose we know simplest Fukaya. How can we get higher Fukaya? And in particular, Fukaya in dimension 1 of the target. Namely for Riemann surface gives chiral fermion. So this is a result of Polishuk. So this is Polishuk. It is very complicated name. It's Russian family name. However, Polishuk is well known among mathematicians. Don, have you heard about Polishuk?
Of course, I heard his name many times.
Okay. So actually, his result that I admire is that the M3 is the Shogu kernel.
And this is invisible what you're writing. Yeah.
It is a Shogu kernel. Or in other terms, it is the green function for the bar operator taking values in vector bundle. And this is a nice relation between M3, so it is Massey operation, and free fermions. Maybe we will discuss this at some moment. What is interesting is that taking this tensor product, you can understand what is the chiral fermion on the product of Riemann surfaces.
Mm-hmm.
So basically, it was what we had to do with Dong before the New Year, before the Chinese New Year. So, okay. Because Dong asked me about this.
Mm-hmm.
Okay. So, I think I will not have time to discuss everything about tensor product, but I'd like to start with dressing transformations and go as far as I could go today without hurrying up. Right, Pasha? Without hurrying up.
Mm-hmm.
And when I say dressing transformation, of course I mean so-called integrable systems. So while people discuss what the integrable system is, so people have different opinion on this subject. Let me try to explain one of the way to look at it. The way that would fit this system. Namely, let me start with the example of how I understand KdV. you have the Schrödinger equation. And then you want to change U, that is potential, in sometimes, or along sometimes, such that its spectrum is the same. It's so-called isospectrum deformation. So you can easily do this. Take operator, say you may take the formal group of pseudo-differential operators and just conjugate. Then you may ask, are we happy? Is it a solution? No, we are not quite happy, because when we conjugate like this, of course the spectrum would be the same, because it's just transformation. However, the form of this operator would not be the same. Okay? It would be some pseudo-differential operator that we are not interested in. So we need to choose very special U's such that we still get operator of this form. Second derivative plus potential. So it is a game how to choose such special U's that we still have the form of one-dimensional Laplacian plus potential. And here we invent some tricks. So for this particular problem, there is one set of tricks. For another problem, there is another set of tricks, just to keep the form that we prescribe. Okay? Okay? Now, how to apply this philosophy to the problem that I'd like to pose. Namely, I'd like to deform this equation. Last time, not last time, several talks ago, we discussed that there is a nice deformation of this equation.
What the equation is, what's the equation? There's no equality sign. It's flatness.
Okay. Equation is that this is zero. Flatness.
Sorry, it's not visible. Sorry. It's not visible for two reasons: out of frame and well, now it's not but now it's out of focus.
It's out of focus. Because I'm sorry. So is it visible now?
Okay, yeah, that's good. That's good.
Okay, this is the equation, and we started solving this equation. Actually, we say that A is d tau, and we have to solve this equation. And actually, we found that there is an easy set of solutions to this equation that is kind of seria of something. Namely, simplest delta A is d tau commutator with something, with some C1. These are constants. You can plug it here, and you can see that this is infinitesimal deformation. Then you also can look, delta A is d tau. You may look in this ansatz. You may call this B. And find that it solves this equation, but exactness of B means that somehow d tau dB equals to 0. So there is another easy solution. B is C2. And so on. So where C1, C2 were some operators, constant operators. Constant operators.
Sorry, what's the difference between C1 and C2? They do the same thing, right? They both deform A by.
Sorry. Delta A was d tau times B. So how to solve B?
There's another commutator with d tau inside.
Yes. So actually, look. So this is a solution. Now let us look at this. The question is it a solution? Let me make a step. Applying d to the left-hand side and to the right-hand side, we come to the d tau dB equals to 0. So look, we have the same equation.
Yes.
So once again, we have partial solution B equals d tau HC2.
Yes.
So this is B, then we plug it here, and we have solution determined by C2. So we have this set. So in this way, we describe the set of infinitesimal solutions, of infinitesimal deformations to this equation. And this space of deformations is given by the set of constant operators. And one might think that these operators are actually Taylor coefficients of some operator valued polynomial C of Z. But these were infinitesimal deformations. So we may try the game to write down abstraction or to look for the explicit formulas, how to integrate this. So it turns out that instead of playing this game of deformations and abstractions, one can solve this problem, namely problem of the deformation of solution to this equation, almost general. And I'll comment what does it mean almost general. Using so-called dressing transformation. So namely, I'd like to show you a huge orbit that acts on there's a huge group that acts on the space of solutions to commutativity equation, and it is basically what I would like to call Giventali-like group. I call it Giventali-like because Giventali studied a bit different equation. I think he studied WDVV. Okay. So since I kind of discovered this group, so maybe van der Leer, no, not van der Leer, because he studied WDVV. So in the context of commutativity equation, I think I discovered this group with Polyubin, with the great help of Volodya Fogg.
Mhm.
Okay. Yeah, so it would be called Fogg-Giventhal group. However, it's published in my paper with Polyubin. So now let me explain this group. I think in some sense this group was already in some QGIS texts. Namely, suppose I have this equation. Then I understand that A is H minus 1 of 1 over the dH. So there is some group element H that depends on 1 over Z, such that this connection is exponentiated like this. Okay? And this is not, so of course it depends. So H is actually function of 1 over Z and also times.
So times are the coordinates of the formal disk where this is a solution.
Yes, exactly.
Mm-hmm. So the camera is really not behaving well. I mean, it's constantly switching to the unfocused mode.
Okay, so let me constantly switching. So thank you, please let me know. Is it okay now?
Yeah, it's good. Well, not constantly, but often enough.
Okay, so please let me know. So, not all H's are good. Like I explained it in the case of KDV. Not all conjugations are good. Because with general H, you will not have this form. And this form means only first order pole. Okay? So we need to find a way to generate such H's that A has only first order pole. So very special. Like in the case of KDV, you need to find very special conjugations that keep Schrödinger equation the same. So the role of this pole was played by the degree of d over dx. Okay? We should get d over dx at the second power, no fractional powers, no inverse powers, exactly d over dx. So this is analogy. Now there is a trick.
I'm confused. What do you want from dependence of A on Z? I mean, in this formula above?
I want A. Sorry. It should be 1 over Z. Okay. I mean the connection. I'm sorry. So I want this thing to have only first order pole.
So A itself should be a formal power series in Z, or
no, A should be Z independent.
A should be Z independent. Okay.
Yes.
Yeah.
So when I write it this way, it could not depend on Z, but for general H, it could have higher order poles.
Right. So not just first order pole, but actually a pure pole. I mean, nothing else. I understood. Okay.
Ah, yes, because it's pure pole. Okay. So idea is the following. So I'll do some computation. Take H 1 over Z that depends on T and multiply it from the right by a polynomial function G. That will be dressing. And decompose it all the way around as H plus of Z, H minus 1 over Z. So you can always do this. At least over the formal disk.
And the two terms on the right implicitly depends on T?
Yes, of course. So this is inverse factorization problem. And later we will decide where to put constant term, to H plus or to H minus. I always forget. So now let us do some computation. Namely take external derivative of the left-hand side and of the right-hand side. So D H G, and I'll also take G minus 1, H minus 1 on the left equals to D H plus H minus H minus minus 1 H plus minus 1. So I need to compute a bit. On the left, I will use the fact that G is T independent. So on the left, I'll have H minus 1 DH. And here I
think
have
the order of pluses and minuses is probably wrong. Probably in the first, maybe H minus minus 1, H plus minus 1.
Here.
Yeah.
Yes.
Probably. Right.
So let me see. So on the right hand side, first I differentiate here. So I get H minus minus 1. Here I have H plus minus 1 D H plus. And here I have H minus. Plus I differentiate here H plus cancels, and I have H minus minus 1 D H minus. Okay? what did I gain at the moment? Important thing is, after this, to
There's also the G inverse dg term on the left, right? Oh, sorry, no, it doesn't depend on t, sorry.
Mhm. So what do I like to have then? I'd like to eliminate H minus. So I'd like to multiply the left hand side and the right hand side by H minus. So I'm trying to explain the idea. You see, I'm always getting confused at this moment. But when I need to conjugate with H minus. And hopefully, when I'll conjugate with H minus, I'll get some simplification. So I multiply by H minus -1 from the right. So let us do it together. Because at this point, I am always confused. I always make here mistakes. So first of all, I'd like to multiply by H minus 1, H minus -1 from the right. So I get H minus 1 dH G H minus -1, and here I have G minus 1, and here I'd like to multiply by H minus. So I multiply by H minus the left hand side and the right hand side. So when I do this, on the right, I have a decomposition. H plus -1 dH plus dH minus H minus -1. So now I'd like to decompose terms here. So here I have this GH minus minus 1. So let me rewrite it in the following way. GH minus minus 1 equals H plus H minus 1, right?
Mhm.
So doing this thing around, and so one second. So I have this. So I want to multiply it by GH minus. So
it's H minus 1, H plus. GH minus inverse is H plus H inverse. Sorry, is it correct? Sorry.
so
Yes. Sorry, H inverse H plus. The opposite order.
so let us see what would I have here. So from this expression, just 1 second. I'm always so so I have this, okay? Then I have this and this. So so I'm trying to get rid of G. Namely, I would like to say that H minus, so actually H minus part in G should go away. Unfortunately, I'm having H plus part here.
It's the formula is and the formula is wrong. So it's the order of the factors on the right side is different.
Where? Here?
No, above.
Here.
Above.
Here.
Above.
Here.
Yes, here.
Here is
It's
wrong.
H. Yeah, the order is wrong. It should be H inverse H plus, the opposite order. No. On the right side, the order was wrong. So the formula is G times H minus inverse is H inverse times H plus. Mm-hmm.
G times H. Like this.
Yes, just the inverse on H minus on the left.
Okay, it's better.
Mm-hmm.
So here I multiply by H. So once again. So I have this formula. Let me see once again. Yes. No, H minus minus 1.
Yeah.
Ah. So, so I have this formula. Okay, so let me do it again. So this guy is H minus 1 H plus.
Mhm.
And if I go all the way around, it should be H plus minus 1 H. Okay?
Mhm.
Okay. So now, taking everything together, I have finally
Mhm.
H plus minus 1. And here I have dH H minus 1 H plus equals 2 H plus minus 1 dH plus dH minus H minus minus 1.
Mhm.
Okay, from this I see that dH minus H minus minus 1 has only first order pole in Z. So actually, I should start with this expression, not with the expression all the way around, but it's the same.
Mhm.
So this expression is I can solve A as G minus 1 dg, and I can solve it also as dg G minus 1 if I inverse G to the G minus 1.
Mhm.
But still, it's what I wanted to get. And it's good that we made it together. Okay? So taking only poles and ignoring positive powers, we have what we wanted. We have found conjugation that keeps the first order pole. Because on the left hand side, so here there is no poles at all. Here the only pole is the first order pole. And H plus means that you are not creating poles.
Sorry, may I ask a stupid question?
Yes, yes.
Because we have this H plus minus 1. So,
H plus minus 1, it's a group element.
okay.
So H plus, there was depending on Z, on positive powers. That's why the H plus minus 1 was also depending on Z. So it's a group element. I forgot to say.
But group element means that it starts with z with zeroth power of z with some invertible
yes,
coefficient.
yes, of course, of course.
Okay.
So this is what we wanted to get. And this is addressing transformation. So it is clear that for G, okay, so for G equals to 1, H minus is H. So actually this was the trick that Volodya Fock told me. And since I have not discovered it by myself, I'm always forgetting this thing. But this is addressing transformation. That clearly integrates the deformation I discussed before. Let me give you an example. So we have an orbit, a huge orbit in the space of solutions. Let me explicitly discuss some particular orbits, easy orbits, okay? So you see, when I'm writing this, you see, I say that I take one solution to another solution. But how does it help, you may ask? Because in order to play this game, it's better to have at least one solution, right? Then you can dress it. So it is the standard problem in, not problem, question in integrable system stuff. Okay.
No, but how to read this formula for the dressing transformation? So you are given some h, you found one solution.
So
and then,
suppose I have some h.
yeah.
And okay, I'll describe this h in terms that dh, h minus, so now now it's to the right, h minus 1 has only 1 over z.
Sure.
And this is equivalent to the fact that that dh h minus 1 is a solution to commutativity equation.
That's good, but then how to read this deformation formula? So then what I should be looking for? So in principle, I'm
Okay,
interested
good.
in. Yeah.
So let us take g of z equals 1 plus zk ck. Okay?
Mhm.
Decompose and then go all the way around. You will have some commutators of elements of H with G.
Mhm. So we need to decompose h times g into this h plus and h minus, and then we want g such that h minus satisfies the property that we liked.
Yes. So how to get it? You have this guy to the right, and you have something to the left.
Mm-hmm.
Take something from the left and commute. So basically you will get some commutators. Actually, you would like to say that in this formula, so we're discussing how to apply it. So let us apply it properly. So this is original H. Okay, so we know what H is. We say that it is H plus, and here we will not write general H minus. We might try to write H minus plus. So we may try to write it as H 1 plus something. So what I actually want to do, I want to take this H, go with this H all the way around. So when I'm looking at the formation of H, I'll have to commute this H with this C. So basically the structure would be something like this. H, C, H minus 1. And it's clear that it will go through commutators. So it's combinatorial formula, and you may play this formula in perturbation theory. You may play this formula in perturbation theory where? In C's and also in T's that are here. So I cannot show that you will get exactly the deformations that I described above. But it's possible to check it. So clearly what you will have is just some bunch of commutators. Also, so it's kind of an exercise. You see, there was nothing to discuss. The only question is to write down explicit formulas. And I have not checked it in general case, but it is doable. So you see, you need to move H through C. You will get some commutators. Commutators of what? Of elements of H minus 1. And this H minus 1 is related to H and to this d tau that I was writing. Or to A. Or you can even write P exponent and decompose it in powers of A. So it's funny, but it works. So you see, it's a bit like Campbell-Hausdorff formula. You are multiplying some exponents, however, you are keeping traces of powers of Z, positive or negative. So if you are interested, you can just check infinitesimal story. You see, mysterious and I would say beautiful, or no, people say remarkable. Remarkable thing is that two different things joined together, integrable systems and topology of configuration space.
Sorry, I'm not sure what you're talking about. What topology of configuration space? There's formal disk here. There's no topology.
No, I mean here. This equation came from the description of factorizable of cohomological field theory.
Mm-hmm.
Namely, we got these coefficients of A from maps to cohomology of LM spaces that are factorizable at the generation of LM spaces. So it was a piece of, you might say, topology, or you might say combinatorics of something.
Mm-hmm.
That's we described like several talks ago when we studied this. Cohomological relations in the space LM.
Mm-hmm.
That's how we got to this. Now it turns out that on the space of solutions, it means on the space of cohomological field theories for LM, there is an action of Giventhal group. And here we have a proof. So mostly people studied Giventhal group acting on solutions to WDVV. There it is much more mysterious. So actually this action is much simpler. Okay? And then if somebody knows Kyoji-Saito theory, you may say that this G of Z is nothing but the action of the group that takes one good section into another good section. I told you that there is no, so maybe Dong knows this, that in Kyoji-Saito theory, there is cohomology of Q of Z. And the question is section, lift. And you can always rotate by something holomorphic in Z. And you may try to look, where does this group appears? So there was some construction, you take cohomology, you construct homotopy, you subtract the image of good section, all that. You are doing something, some procedure. So there was Kyoji-Saito connection here. So you may ask, suppose you have the same system, but different section. How could they differ? They should differ by something that depends on Z. They depend on this. So, Giventhal group in this context, I don't know how to call it. Saita, Giventali, Fogg, Losev group. Okay. Many people. From the point of Hyoji Saita theory, it's a choice of good section. Now, we will get such structure. The question would be, would this matrix be symmetric with respect to some pairing? In other terms, would this connection preserve some pairing? Now we know when it happens. It happens when this G is not from the general linear group, but from orthogonal group with respect to this pairing. Almost up to some Z2 minus Z shift. So what Hyoji Saita was doing, he was looking actually for such G, for good G. So he called good G good sections. And then Hyoji Saita was always surprised why he cannot get a single good section. And here it's clear that from these axioms, there is no way in general to get a good section if you do not impose some other conditions. And some other conditions could be like some homogeneity. But if you have homogeneity, it means that you have this rotation, but you need to look at this rotation that is compatible with homogeneity. And again, Hyoji Saita was missing good section because there is this group. Okay, so I explained how this thing is related to Hyoji Saita theory. So there is no way to have something canonical. Still, let me go to the issue of special orbits. Could you guess the simplest solution to commutativity equation? So if you follow me, you should get it immediately. So once again, commutativity equation says that A I dti aj of t dtj, that this commutator equals to 0. No, that this is 0. Okay. Let me put it this way. So these two things commute, and also dj ai anti-symmetrization equals to 0.
Oh, 0 is a solution.
Okay, but it's too simple.
Well, then pure gauge is a solution, as we were writing down all the time.
Pure gauge is not a solution. Pure gauge solves here, but pure gauge is not a solution in general. But there is a simple solution. If you just keep in mind that AI of t corresponds to AI plus AI j tj plus etc. And this AI corresponds to this space. And this Aij corresponds to this space, etc. So simplest solution is when you do not have higher operations. Okay? So it means that A is constant. AI is constant. And let me call it phi I. Then second equation is clearly solved. What about the first equation? We say that phi I, phi j, commute. Pasha, what's wrong?
No, everything good.
So then, how can we get this h? Then h, easy. Okay. I pretend that I was in the United States. Easy h is e to the ti phi I over z. When phi I commute. So it is easy. Now, in order to get more complicated h, we can just dress this easy equation. So let us dress it. So these are easy equations. So this is a particular case of equation that goes through this point where you do not have higher structures. However, you may ask a question. So first question is, could we always go through such point? Through easy. So there is an orbit. So this has to be studied. At least I can propose to you the huge number of solutions. I am not claiming that they are all solutions. I don't even know how to prove that that you will always have such solution. However, there is one remarkable case. Special case. If phi I, if the algebra generated by phi I is semi-simple, so semi-simple means there is a basis EA in span phi I such that EA EB is delta AB EB. Okay? In this case, one can check that all deformations of such solution are addressing transformation. Okay, so I'm not going to give classification theorem, because when you have a classification theorem, it is the end of science, right? So classification theorem is the grave of the subject. When you classify, you basically kill the subject. Nothing interesting. Okay.
When you say semi-simple, does it mean generically semi-simple or really semi-simple?
I mean really semi-simple. I mean this. Okay, so you may say that everything is actually supercommutative, and in supercommutative case, one has to rethink it, but you see, I am not going to give classification. I just show the huge space of orbits. Okay? So, now we need to have a break. Because after the break, I am going to discuss tensor product and formulate conjecture that tensor product is compatible with dressing. And this is interesting. Because Kyoji Saito never studied this. He studied tensor product, but he didn't study it this way, as far as I understand. So I'm always referring to Kyoji Saito, or when I can generalize or say something that is new for him. Okay, so let me see the timing. So I actually wanted to, oh my goodness. I wanted to be short. So we need to have a 10 minutes break. So I thought I will talk for 2 hours, but Pasha, was it, I don't know, helpful or was it understandable?
I don't know. I'm having troubles understanding this dressing transformation, but that's my problem. I just need to. Yeah, I'm sorry.
No, you see, I tried my best. So maybe, Pasha, if you ask, so if you have problems in understanding, it means that there is something that looks strange or looks weird
Yeah,
or looks.
I guess not enough. I would like an example, but yeah, I don't know.
Example of how it works.
Yes.
So we had infinitesimal example.
Yeah.
So
Yes.
So okay, here we have an example. Okay, let me give you an example right here in this simple case.
Yes.
E to z. It could be anything. Z, K, C, K matrices. So let us do the dressing. We take phi to the right, C to the left. So in the first order, we have the following term. So I don't remember, do I have K plus 1 or not, but so let us see what we have. Let us concentrate on the T squared term, okay? So T squared term in this particular model would correspond to the simplest operation, simplest higher operation. So how should we get it? We should expand. This is 1 plus Ti phi z plus Ti Tj phi Fj over z squared. So we are looking only here. And here we have 1 plus zk ck. So basically we can look at the first order of this ck. Okay? So let us consider small dressing. Dressing that is close to 0. So we took something to the left, something to the right. And then we want to have what? We want to look at H minus, right? So 1 over z, we want to take 1 over z to the right. It was at the left, we need to take it to the right. So here we have z1, c1. It's the only place where we can have 1 over z. And there is also a constant term. But we want this dh minus h minus minus 1 to have first order pole. So we are interested in this. We need to take this bracket to the left. Okay? So we will get something like C1 phi I phi j. I think we will have this term. And here we have 1 over z. So this would be the first higher operation. You see, it clearly has two indices downstairs, I and j. And it depends on this matrix C. Actually, if you just think what kind of construction you can get, having one matrix and commutative algebra, the only thing that you can have is a double commutator. Look, you have three matrices, okay? Phi I, phi j, c. You want to have a word that is, let me see, should it be symmetric or anti-symmetric? It has to be symmetric. So the only other option would be something like this, but I think this never happens. So actually this thing, I think this thing happens. Sorry. You have commutator of C with this. So from this formula, you have commutator of C with phi. So you see, at least I'm trying to explain to you how one can compute first terms. And in the article that I published with Polyubin, we computed some terms. And you can just take these terms and check term by term that they solve these quadratic equations. And you will find that they solve it because phi commute with each other. So it will be the first dressing of commutative algebra.
Yeah, sorry, I still don't know what are we talking about. So what is the result of dressing?
I am taking this product.
So the output of dressing is the left-hand side of this equation, or the right-hand side, or the part of the right-hand side?
The output of dressing is something in the box. So I need to find out H minus and take this log. It's clear that I am taking here a log, right? I am taking matrix log. So after I find H minus, I need to differentiate, take inverse. So here I'm trying to compute this H minus. I'm having this theory in one of these. I'm having this something in these. And I am taking this, okay. I'm trying to take this to the right or this to the left. Or I just multiply and I am just trying to see what terms do I see.
So yeah, sorry, Andrei, I think that you, at least I don't I don't quite understand this procedure of factorization that you are constantly referring to, that you are supposed to reshuffle something to one side, something to the other side. I can probably do it for a monomial.
So there is a unique way. Okay. So it is a standard theorem that there is, so if you have two parabolic subalgebras in the algebra, or two parabolic groups, that's a kind of opposite, you can always put general element taking one element to the left and other to the right.
Mhm.
Okay, so just imagine that you have two type of generators. Positive, you call one generator positive, and you call other generator negative. Okay. In the Lie algebra. Okay. Suppose we have a Lie algebra. Call it G. Suppose G is decomposed in two subalgebras. So G plus is a subalgebra and G minus is a subalgebra. However, if you commute G plus and G minus, you can get either here or there.
Mhm.
Okay?
Yes.
Here you have generators T plus with some indices I plus, and here you have T minus, okay, with some indices I minus, okay. It's better to write it like this. There are indices I plus and I minus.
Mhm.
I plus span G plus and I minus span G minus. Then the general element of the group is e to the what? Lambda I plus Ti plus plus lambda I minus times Ti minus. I'm sorry, I have a call. Алло? Алло? Да. Алло, я тебя слушаю. Гриша? Алло. Что? Нет, ну я самое... Я немножко затянулся, поэтому я думаю, за 10 минут я закончу, за 5 минут я выйду. Еще раз, за 10 минут закончу, за 5 минут оденусь, за 5 минут дойду. До точки на время. Okay. So, suppose I have this.
Mhm.
Then I can using Campbell-Hausdorff formula, decompose it into some lambda tilde t plus, lambda 2 tildes t minus. And this is a desired decomposition.
I see.
It is just inverse to Campbell-Hausdorff formula.
I see.
You know, unfortunately, I have a call, and you see, I have to go in 10 minutes.
Uh-huh.
So, because I have to teach in another place. So that's why I wanted to keep it 2 hours. But still, I'm trying to explain. We should make this decomposition. If you consider Campbell-Hausdorff formula, it goes from right to left. This formula is invertible.
Okay.
So this is this factorization. The group that I'm talking about is a group of functions of z and z minus 1. A loop group.
Yes.
And here is this factorization.
So I have small questions about the formula you write down on the right below the board. I think you erased the part of the formula, but it involves. Okay, maybe it's just an impression, but I feel that the formula you write seems to be generalized as a sum over 3 valent trees. And it looks like a homotopy versions of the algebra. They're coming from the homotopy of the algebra.
Unfortunately, so it's a good point to relate it here. But we were looking how to get it in terms of the tree, but it's not actually a tree. It's something like this. So it is kind of not homotopially algebra, but something with higher differential. However, I do not know exact relation here.
So you put your starting matrix on the left end and keep applying the matrix on the vertical branches.
Something like. Because when we were writing formulas, I remember, when we were writing formulas, we were not thinking too seriously, I think, about homotopical interpretation. And then I always had a feeling that this G, or this dressing, should be understood as some kind of homotopy. But I never made it precise.
Okay.
So in this particular case, structure is like this, seems to be like this.
And I think you are almost there and almost on. Okay, how do we get this integrable hierarchies from this formula?
I am not saying that we are getting integrable hierarchies from this formula.
Oh,
I'm saying that we have integrable structure here.
Integrable structures. Okay.
So I try to explain what I mean by integrable structure. By integrable structure, I meant a situation where you have conjugation. and you are keeping a special form.
Yes.
Okay, thank you. Yeah.
Okay, and unfortunately now I have to go. So tomorrow I'll discuss tensor products and compatibility issues.
Okay.
Okay. So we are not in the hurry, so we can. So after we studied so much about this LM spaces and its topology and all this, we should we can formulate conjectures that are not proven yet. So the one who proves it could publish it. Okay. Okay. So thank you. Unfortunately, I have to go to have another teaching. Extraordinary teaching. So it kind of interfered with this.
Yeah, no problem. And see you tomorrow. And thank
See you
for the-
tomorrow at the
you.
standard time.
Okay. Thanks a lot. See you
Bye.
tomorrow.
Bye.
See you tomorrow.
Bye.